Hello everyone, this work is about using neural vocoders to create the training data for speech spoofing countermeasure. Nowadays, speech communication is widely used over the internet, but there is a risk that attackers can use text-to-speech or voice conversion technologies to clone our voice. To protect the users, we may use a spoofing countermeasure. In this work, we use a machine learning technique to build a binary classification model. This model can automatically classify whether the input speech waveform is uttered by a human being or being synthesized. We follow the standard way to build the countermeasure. First, we find the training set to train the countermeasure. Then we need a test set to measure its performance. So many databases are available for training and testing the countermeasure. For example, the databases from the ASVspoof challenge, and also other challenges. All these databases contain multiple TTS and VC conversion systems in both training and test set, so this is good. However, all the databases are quite small compared with those used for speech recognition or speaker verification. One reason is that building diverse TTS and VC conversion systems are not that easy. While we have open source implementations, for example, for Talkatron, Transformer TTS, and so on, we may also need to include more diverse systems, such as those from based on unit selection or hidden markov model. Furthermore, we need high-quality data pairs of text and speech from many speakers. Sometimes we also need linguistic knowledge and text analyzer and so on. So it's not that easy to build diverse TTS and VC conversion system. In the case of ASVspoof 2019, it took 6 months in order to build one single TTS system. So in this work, we want to ask whether there is an easier way to create spoofed data without using the full-fledged TTS and VC conversion system. Can we reduce the time cost to build a single system from 6 months to just 2 days? The method we propose in this paper is to create spoofing data using neural vocoders and copy synthesis. Before explaining the copy synthesis idea, we record that a typical TTS system needs an acoustic model to convert the input text into the acoustic features, such as male spectrogram, F0, and so on. Then a neural vocoder is used to synthesize waveform. The idea of copy synthesis is to remove the acoustic model, extract the acoustic features from the talked waveform, and reconstruct the waveform. It's called copy synthesis because we copy the acoustic features directly from the talked waveform. This process is also called a vocoding process. The copy synthesis data can be considered as data from a TTS system with a perfect acoustic model, but it still contains artifacts from the vocoders. That's why it can be used to train the countermeasure and the spoofed training data. So notice that the acoustic feature extractors are usually deterministic. For example, we can simply extract the features using STFT and a filter bank. With the copy synthesis technology, we can easily create the spoofed data for the countermeasure training set. We use the bona fide training data as the input, and we use the copy synthesis waveform as the spoofed data. One advantage of using this technology, as I mentioned, is that the neural vocoders are easy to train. They don't need text or linguistic resources. Many neural vocoders are also fast to synthesize. One additional advantage is that the vocoded utterances are timely aligned with bona fide data frame by frame. So based on this property, in the paper, we proposed a frame-level future contrastive loss, which was found to be helpful to train the countermeasure. Given these details, we would like to ask a few questions in this paper. The first question is the copy synthesis data useful for the countermeasure training? A further sub-question is to ask whether there is a good way to train the neural vocoders in order to do the copy synthesis. We can directly use pre-trained neural vocoders, or we can train them from scratch using the bona fide data included in the countermeasure training set. Or we can fine-tune the pre-trained neural vocoders using this bona fide data. The second question, as I mentioned in the previous slide, the vocoded data or combinations data is timely aligned with bona fide data. So whether we can find a good way to take advantage of the alignment between this bona fide and vocoded data in order to better train the countermeasure. So this would be the second question. So for the experiment, we prepared different versions of a training set. The first one is a conventional training set from the ASVspoof 2019 LA database. It includes bona fide data and different types of TTS and VC conversions. Next, we prepared the training set using the vocoded data. We used 4 types of vocoders to create the vocoded data: high-frequency neural source filter waveform model, their combination, and wave glow. In order to better measure the performance of countermeasure, we used multiple test sets. We test each countermeasure using all these test sets. The countermeasure has the same architecture using the wavevect 2.2 front end, followed by linear output layers. Here are some highlighted results. On sub-question 1, we found that it's better to fine-tune the pre-trained vocoders using the bona fide data in the countermeasure training set. The vocoded data created from such a neural vocoder lead to the best performance in our experiments. On sub-question 2, we found that a contrastive feature loss can improve the countermeasure performance. This training loss encouraged the hidden features of the bona fide waveform to be close to each other. Also, the hidden features from the vocoded waveform to be close to each other, but it will push the features from bona fide data away from the vocoded data. Combining the findings from these 2 sub-questions, we found that using the vocoded spoofed data can train a good countermeasure. Here are the equal rates achieved by the countermeasures trained in our experiments on multiple test sets. I just want to highlight 2 columns, the left columns and the right columns. So the left columns correspond to the countermeasure trained using the ASVspoof 2019 training set, using TTS and VC conversion spoofed data. On the right-hand side is countermeasure using the best vocoded training set in our work. Also, it used the contrastive feature loss. So you can see how the countermeasure on the right-hand side achieved a lower equal error rate on most of the test sets. For the detailed results, please check our paper. Also, you can find the appendix with additional results. We released the training set, the code for the vocoders and countermeasures in our GitHub. Please have a check.